Welcome, everyone. I'm very pleased to introduce Gert Lanckriet, and although I might be saying your last name wrong, correct it if I said it wrong, from UC San Diego to talk about music recommendations. So we know we're going to have fun because we're talking about music and recommendations. He has a very impressive record, academic record, I should say. We're talking about music, so you might think I meant musical records.
Yeah, no.
Yeah, maybe he'll sing for us.
I don't think we want that, but yeah.
But including a Sloan Fellowship Award, which is quite impressive, a CAREER Award, and he checked off all the other boxes we as computer science faculty are supposed to get, but also a SIAM Optimization Prize in 2008, which sounds very cool and very complicated. And he heads the Computer Audition Laboratory at UC San Diego, as well as working on computational statistics and machine learning. He's also a co-founded Benefunder, which he might say a few words about, which is a very innovative idea about how to get research funding into the hands of faculty members from people's investment portfolios. Very cool, fighting an uphill battle to get it through various bureaucracies, but I hope it succeeds. But let's talk about music search and recommendation, and let's give him a warm welcome to the UC Berkeley iSchool today.
Thanks. Thank you, and yeah, thanks for having me and inviting me in this very nice room. This is really cool, actually. I was just telling you. So that is actually true. So I do direct the Computer Audition Laboratory at UCSD. One of the interesting things about lab names is that the name never changes unless you do an active effort to do that. But that kind of doesn't often happen. So the name is still there from 10 years ago, but I would say that the lab has come quite a way since then, and there's certainly quite a lot of other things that we are doing nowadays too besides music. So I'm going to focus mostly on music, but I'll tell you a little bit more about some of the other things that we're also doing. But kind of like this somehow was the starting point. There's lots of music content out there. In fact, I personally kind of experienced this when I arrived at UCSD 10 years ago now, after doing my PhD right here in Berkeley. Some of my students seduced me to play music with them. And I kind of understood quickly why that was. They wanted to build a music room somewhere, and what better than a faculty's garage, right? And so we started to record and upload stuff into MySpace and things like that, and quickly realized that there's lots of audio content out there, lots of music out there, and especially on MySpace, which I didn't draw on this graph here. There was at the time, this is now 10 years ago, there's tens of millions of songs on there, and less than 1% people actually listen to. And so we realized that we're like, hey, we're uploading our content into MySpace, but realistically nobody will ever listen to us, right? And so somehow that was really kind of the initial motivation, so to speak, for this research here, because we were looking at each other and saying, like, can we do something about it? Not because we're necessarily good, undiscovered musicians, but there's a lot of them out there on MySpace that probably are actually really good, but still nobody's discovering them because it's very hard to access that content. And there's a lot of it out there. I mean, you don't necessarily look at the horizontal, like the numbers on this axis here. There are, maybe a couple years ago now, but places like Amazon MP3, Spotify, and iTunes, we're talking 25, 30 million songs that they have in their catalog nowadays. As you can see, Pandora is a little bit less. One of the reasons why that is because they actually use humans to tag each song in their database, and that clearly is a pretty slow effort sometimes. But anyway, so for us, this was really the starting point. I mean, it's about, there's tons of, musical content out there. How do we actually, bring that to the consumer, and how do we let people discover this, especially a lot of the music that, they may otherwise never find, right? And so, to kind of start this as a research project, there was two cases specifically that we focused on, which kind of are, an interesting way to cast a research project around this. One case is this query by example setup, where basically, you start from a set of query songs or query audio snippets, 1, 5, or 10 of them, and then you expect, the algorithm to return you a playlist of 20 or 50 or 100 songs or something like that are similar to that. And then the other use case that we got interested in, again, specifically to formulate this as a research problem is, given a text-based query like, rock with screaming vocals, can you, build an algorithm that will pull from, a catalog of 1 million songs, kind of the most, relevant songs for that type of query, right? So this is how it all started. But to be honest with you, being pretty applied data scientists and kind of always thinking about like what are the real use cases here, I have to admit that these two first cases here are mostly kind of academic importance. I mean, nobody is going to type a Google search query to find music, or even like providing seed songs. I mean, who really wants to do that? No. By the end of the day, what users want to do is they just want to enter their car or pull out their phone, and the right music should just start playing to them, right? But the thing is, these two more kind of academic cases here will allow us to understand music content, to figure out how can we annotate music, how can we figure out things like musical similarity, and so on, and then really kind of from a practical perspective embed that in these very practical use cases. Where if you think about it practically, very often an important factor as well is context, right? What is this person doing? How are they feeling? And that's the kind of information that you would like to get access to if you're gonna try to give them recommendations just out of nowhere without a search query, right? Because that's really where we want to go with this. We want to actually have recommendation systems that recommend content without a search query. It just comes to us. Right, and so one of the things you want to know then is that user context. So how do you get there? Well, nowadays the cool thing is that more and more there are all these kind of naturally worn sensors that we have on us, whether it's our phone, maybe a smartwatch. I'm not talking about like Fitbits and so on, because these are kind of like, not everybody has them, but I'm really talking here about sensors that, you can imagine, like a watch and a phone at least, that everybody just has naturally already. But even all the way down to like kind of very creepy details, like, the tweets that people or the text messages that people write from their phones can tell a lot about, what are you doing, or, how are you feeling, right? And so anyway, so although we started as the Computer Audition Lab, nowadays we actually do quite a bit of work on, these type of sensors to try to figure out activity and mood of the user to then use that for, these recommendation problems. Now, as a couple of side notes here, so as I said, so we have come a long way. There's other things that we work on than just music. I'm going to really talk about these today, but I just want to quickly mention them. So one of them is video. Starts as music, kind of start to look into environmental audio, and then at some point realize that actually one of the things that a lot of people that work on video are not doing is listening to the audio of the video to try to figure out what is happening in that video. Okay, and so we started to do that and basically integrate audio and visual information to understand what videos are about. And what's very interesting is actually if you listen to a video, there's a lot you can tell about it already in many cases, except if it's like, if it has like a soundtrack that is overlaid, then, of course not. But otherwise, there's actually a lot that is encoded in the audio signals. So what we started to do then is, can we, process the audio of the video to get a good idea of what may be happening in the video, and then selectively process, the visual content of that video in a very efficient way, rather than processing all the visual content, right, to really figure out what's happening in there. Now, this actually, we did some work on that, in the lab, but most of this actually spun out of the university into a startup company called Kivio, which one of my students started. So this is kind of like more going into the commercial space now to really, analyze the video content that is out there for a variety of applications, including, advertising, recommendation, and, things like that. Where, very often if you look at online video, there's a lot of text around these videos, but it's not always very informative about what's happening inside the video. And it also doesn't tell you what is happening when in the video, right? So that's really what, this technology is basically, doing by analyzing the actual audio and visual content. Another side note here is that, as we started to look into all these wearable sensors, it didn't take very long before, so at UCSD we have a medical school. So people from that school, from several groups actually started to approach us because they were really interested for a variety of medical applications. The fact when you can track the activity and the mood of a person, you can follow up patients after surgeries, you can kind of track, mental health, you can predict when, a dementia attack or, an alcoholic may go back to the bottle, these kind of things, you can predict that. And so there's a lot of applications there, in the mobile health space, which I won't have much time to talk about this today, but this is certainly also a very exciting area. Now for us, the opportunity in these collaborations lies in the fact that many of these medical collaborators have access to patient populations, which allows us to collect data to actually build the right machine learning algorithms to derive knowledge from what these sensors and these all these wearable devices are picking up, right? And then finally, as a side note here too, Marty already mentioned it before. You may wonder what this slide is really doing here, but the reality is that the music project for me was really kind of the starting point of this Benefunder funding venture that I started a couple of years ago. And the reason for that was that when we initially started the music research, we were looking for funding for this very kind of interdisciplinary, early stage, high risk research, right? And I tell you, if you go with something like that to the National Science Foundation, it can get pretty challenging to get money because it doesn't quite fit well, right? And so in my case, I have a kind of longer term background in data science and machine learning, so I kind of went that route to raise money from the NSF. But still, it always stuck with me that I couldn't find funding for exactly what I wanted to do. I had to do something kind of different and then kind of juggle around the money a little bit. And so kind of ended up after lots of left and right turns with this idea to tap into philanthropic dollars. And this is huge. NSF has an $8 billion budget, NIH has a $30 billion annual budget. Philanthropy annually in the US is between $250 and $300 billion. It's a huge pot of money, and today only less than 3% of that is actually making it directly into research. So there's a huge opportunity there. What we developed is a platform to actually tap into that. Not at all a crowdfunding platform, by the way, because crowdfunding only accesses very small bits of money, but totally the opposite. We're going to the top 2 or 3% wealthiest Americans by working with wealth management firms. And through these wealth managers, we're getting to their clients. And you know what? What we're building for the wealth managers adds a lot of value for them because number one, they currently don't really have a good philanthropic service to help their clients with. And so they all want something that the other one doesn't have, so they're very interested. And number two, the way that this is structured on the back end allows them to keep some assets under management for a little while longer. And if you know anything about wealth management, they want to manage assets because they make 0.5% or 1% per year on that, right? More than happy to talk more about this offline, but the idea really here is that on the back end, this actually is nothing but an eHarmony matching platform where the wealth manager brings in the profile of their client, and what we have is a database currently with a little more than 600 researchers from all the top schools in the nation, and we basically just match researcher profiles with donor profiles based on research interest, personal background, and all these other elements that hopefully will lead to an engaging long-term relationship where the donor cuts checks on an annual basis, not just for one single project or something like that. And so clearly my interest on the back end there is really music recommendation is, you're thinking about similar songs. In this case here, you're trying to, match people, which actually happens to be something that turns out a long time ago, I was a consultant with eHarmony when they started to move from more ad hoc algorithms to kind of, machine learning based algorithms for, introducing people to each other. So somehow kind of, related with that background as well. But this is certainly also a project I'm very excited about. I'm happy to tell more about offline. But anyway, so kind of back to, the starting point. So now it's like, 2006, 2007. And so where all of this started was like, with this project here, how can we build a black box that can listen to music and automatically tag it, okay? That was kind of, step one. And so basically the idea here is you have a dictionary of, tags from, a variety of categories. And so what you want to do is you want to basically feed an audio waveform into it, right? Black box being computer algorithms, and then automatically associate that audio waveform with, the words that are relevant, to that song. And if you do that for, a million songs, or 10 or 20 million songs, this was what we initially wanted to do, just scrape all the songs from MySpace and feed them through that, right? Then you can start doing recommendation either based on a word-based query, right? Happy rock for the gym. You just basically match the tags directly, and you build a playlist of songs that have the best tag matches. Or given a song as a seed, then basically you just look at the tags of the song, and then you match it with songs that have similar tags, and you use that to make recommendations. In fact, that is exactly what Pandora does. They just do a simple kind of tag-based distance. But the big difference is that they obtained this big table here with human effort, not with computer algorithms, at least up till a year ago. They're now kind of starting to change that. But that's one of the reasons why their catalog is fairly small, and some people sometimes point out, so to speak, that some of these playlists get a bit more repetitive. Anyway, so how do we do this? Well, so what's inside the box is basically signal processing, machine learning, kind of the traditional approach where you collect a bunch of training data, for example, example rock songs, and then you try to find patterns that all these songs have in common. And then if you detect that pattern in a new song, then you decide that it's a rock song, right, at a high level. But at a more detailed level, so the way this works, and usually what I like to do is go close to my slide then, but there's a little bit of an angle here, right? So let me go here maybe. So to give you a little bit of an idea how we do this, so it all starts with this, the audio waveform, right? So the first thing we do is we chop it into like little pieces, each of these pieces being maybe like, between 50 and 200 milliseconds, something like that. And then for each of these pieces, we extract some features, frequency, and et cetera, related, like for example, here in this case, delta, null frequency, capsule coefficients. So it's a bunch of, audio-related features where then in the next step here, every piece on the left-hand side is now represented by one green dot in this feature space here. So, which is, high dimensional, right? So now this song here, eventually gets represented by, a cloud of green dots. Yeah. Cloud of features, feature vectors, each of these feature vectors describing one little piece. So now you have this cloud here that somehow is representing your audio waveform. And so what you can do then is you can try to somehow represent that cloud of points in a more compact way by, like, let's say, fit a Gaussian mixture model on it or something like that, right? So that's basically kind of like at a high level how you could approach things at a song level. And then if you now want to model tags, what you're going to do is you're going to first look for a training data set, basically a bunch of representative examples of rock songs, right? And then you do the same thing, like you extract all these features, you just pull them all together, and now in this case, the shape of this cloud is going to tell you something about what is characteristic in this audio space about rock songs, right? And so then in this case, you can also fit a model on that point cloud to statistically characterize what rock is about, so to speak. And the reality here is if you start working with a lot of data, so for example, if you want to fit a Gaussian mixture model to this cloud here, you can use expectation maximization, standard algorithms. But the reality is that if you start working with a lot of data here, this can become computationally intensive. And so one of the things that we worked on is a hierarchical EM algorithm to do this more efficiently. And basically, what that does, just at a high level, is we would fit these models for each of the songs individually, and then build some sort of, it's kind of like a clustering algorithms for each of these models to somehow kind of summarize all these song level models into a higher level tag model, but in a way that it's well regularized and of course is also kind of a good model for this tag the feature cloud as a whole, right? And so that has a lot of interesting advantages, including computational efficiency, regularization, and things like that. I'm not going to dig into details here, but the point is when you're dealing with millions of songs, then you need something that can kind of crunch that data, right? So anyway, so once you have these models, you can do the same thing for a whole bunch of tags. And so then when you have a song that you've never heard and the computer has never heard, you do the same thing. You chop it into pieces, you extract this feature cloud, right? And then you kind of just see how well it matches with each of these models to then decide how applicable each of the tags in your dictionary is, right? And so we do that, and so eventually, at least initially, we ended up with a dictionary that probably has about 200-300 tags in different categories like emotions, genre, instruments, usage, like good for dating, good for working out, things like that, vocal characteristics. So what's interesting here, and this was certainly like when we did this, there was already somewhere that people started to do on like specific tag subcategories. But when we launched this was really kind of like a first effort to really look at like just a dictionary of very broad types of tags. Thinking about the use cases, right? I mean, some people may be, specifically looking for certain genres, but other may be like, I'm coming home, time to go to sleep, like, give me some music that is good to chill, right? Well, then, you need a usage tag, for example, right? So anyways, So that was kind of like our starting point. And now to tell you a little bit more about kind of what happened after that starting point, some interesting problems that we bumped into, for example, one is the following. So going back to this Gaussian mixture model that is modeling this, green cloud here, right? So what happens if I, take all these little pieces here of the song and I randomly just shake them around, like permute them, right? So what'll happen? Well, that stuff will get all shaken around, but here on the right-hand side, nothing changes, right? Right? There's no temporal information there. So one first thing that we had to somehow do is figure out a way to take these temporal dynamics of a song into account. And so what we did is we took a bunch of these little blue pieces and we glued them all together into 5 or 10 second segments now, and then modeled each of these segments as a sample of a linear dynamic system. You could call it a dynamic texture model or a Kalman filter. And that's basically what it is. It's like an HMM with continuous states here. So where you have a layer of observed variables, each of which characterize the spectral characteristics of these little pieces here, right? Timbre, harmony, and things like that. And then you have a hidden variable here that varies over time according to a linear equation and models the temporal dynamics, things like rhythm and tempo and so on for these observed variables. Now, of course, first thing here is that when you're going to model a song, you're not going to be able to model every 5 to 10 second sample, with just one of these Kalman filters. You need multiple. Like for example, the intro may have very different linear temporal dynamics than like the guitar solo, for example, or the outro of the song or the chorus, right? So what you need to do is you need to kind of model these songs as a mixture of these dynamic textures. And so then eventually what you end up with is like a statistical model that is basically a mixture model, but now each of these mixture components is not like a Gaussian, but it's like a Kalman filter, right? And then basically as you kind of, so this is the song from left to right where, along the vertical axis here we're just, with colors representing the spectral content, right? The frequency content, the energy in the different frequency bands. And so basically kind of like what happens now is that so this red rectangle here is again one of these 5 to 10 second segments that we're looking at. So basically each of these 10-second segments is most probably generated by one of these mixture components here. And as you walk through the song, you'll see that according to these different colors here, the mixture component, the temporal dynamics, so to speak, that are generating the audio content in that specific segment, kind of changes from time to time a little bit. And it's actually very interesting. Initially, we built this just to model the temporal dynamics in a song. Then as we were fitting these models to songs, it turned out that, this was actually kind of implicitly segmenting the song into different types of, intro, outro, choruses, guitar solos, things like that. And so then we wrote a paper about how you can segment songs with these models, although we never really intended to do that, but it was just a very nice side effect. And it's actually pretty clean even. You don't have to do too much post-processing to do a pretty nice job. And then, as you go through the song, so as I said, like, different mixture components will, generate the audio content in, different segments. And so that basically kind of, allowed us to, kind of take into account these, temporal dynamics. However, that said, still, so this was step 2, now step 3, is the fact that we still have to make a choice here. You have to either choose you're going to use, a Gaussian, for example, to model, your songs, or you're going to, and in your tags, or you have to take that, dynamic texture mixture model, right? And also for each of these models, you have to choose a time scale, right? I mean, how big are these little blue chunks? Are they 30 milliseconds or 200 milliseconds? I mean, it's resolution, right, in some sense. And so one of the things that we observed was that, this is a table of F scores, so annotation, basically performance, for these two models. So this is the GMM model, this is the DTM model. And as you can see, for some of these tags, it turns out that having the temporal dynamics in the model, really kind of, helps you to gain, performance. But then, for others, like for other tags where, the temporal dynamics are a little bit less important and where just the immediate temporal information, right, actually seems to be, enough. And then what you sometimes get is that the dynamic texture model, which is a more complicated model with a lot more parameters to estimate, sometimes it actually doesn't perform well at all. just because there's an overfitting or something like that happening. So the bottom line here really is that there are certain tags for which we see that this dynamic texture mixture model with that model's temporal dynamics really buys us. Well, I have to go to this column here. It's a little confusing because of how I wrote it here, but so this column here shows that the dynamic texture mixtures is really giving us an upside. Then for other tags, it seems like just going with that temporal Gaussian mixture model picks up on instantaneous harmony and pitch and things like that, is actually doing better. So then the question was, is there like a way to kind of combine the both worlds somehow and kind of always have the best of both worlds? And as I said before, so there's also this issue here, like if you have a large number of parameters like in these dynamic texture mixtures, that sometimes you just overfit, and that's where you get not so great performance. So at that point, so here was an idea that we had for a different approach. So instead of, there's two steps here. So you have your audio signal. The first thing you do is you extract features from it, right? And then you use some kind of pattern recognition algorithm, like what we were describing, to model what are the characteristic features for a certain tag, right? Like rock. And so then you can, if you think that temporal characteristics will be most revealing, then you can use a GMM. Right? Because again, GMM just looks at these little pieces, so it looks at very like instantaneous audio information, right? Like pitch and tone and stuff like that. You can do a GMM with a different time resolution. But if you think that temporal dynamics like rhythm and tempo really matter, then you'll do one of these dynamic texture models, or maybe even a mixture of HMMs. You can do that too. That's one of the other models that we've also built. But again, then you always have to choose. However, the idea here was, what if we just consider all these models at the same time, but instead of choosing them here at the modeling level, is there a way that we can combine all these models at the feature level? This may sound a little bit confusing, but look at this here. So for document retrieval, bag of words, very standard approach. Basically, you start with a dictionary of words, and then you count whether these words occur and how often they occur in your document. And then you represent your document as a histogram over word counts, right? So what if we now somehow came up with a dictionary of acoustic words, right? And counted which ones occurred in the songs and how often they occurred to come up with a similar histogram representation for these songs. So now, what you can do is you can actually start with a dictionary, basically a codebook of, a variety of acoustic words. Now, what's interesting here is that these acoustic words that we're considering here are not like prototypical waveforms, but they're prototypical models that somehow statistically represent these prototypical waveforms, right? And so we're considering all these different models, at different time scales. So like the size of the font is kind of indicating, the time resolution that we consider for these little blue chunks, right? So start with a large dictionary of these, generative model instances, right? Different time resolutions, etc., etc. And then count those. So now, like, let's say when you have a song here, right? You can then say like, well, this little 50 millisecond segment is most likely to be generated by this Gaussian here, and maybe this sequence here with a certain time resolution is most likely to be generated by this, code word. And then similarly for, another code word here, which has a very different time resolution of looking at the signal. Okay, so what we're doing now is we're basically kind of counting. Now clearly, like, here in this case, like a text document has one word after the other. In these audio signals, you can look at one piece of audio in like different time resolutions, so some of these words could be overlapping and things like that, right? But the point is what we're doing now is we're counting these, model occurrences, in the audio signal, which allows us to consider kind of the modeling power of all of these at the same time. Okay? And so now, as I said before, so what you do is you basically count the occurrence of these acoustic code words, and then you end up with a histogram of counts of these acoustic words, in the signal. And then the question?
So for each segment, your draws from one of these models. It says it's coming from the model, and then that.
Yeah, exactly. So basically what you do is to assign count +1 to a certain model, you want that model to be the most likely one to have generated this little piece of audio content at that given time resolution. Yeah, correct.
Substance used to be the mixing up different base sets, right?
Correct, you do. And you basically, it's kind of like you have multiple code books in parallel that you're looking at. So you're not just choosing a unique winner. Correct, yeah. That's true. And so then, what's nice about this is that, once you have these histograms, then you're all back to the, the world of text classification algorithms, right? So you can just take, a fairly simple algorithm from that space that can do bag of words classification. There you go to build tag models, right? And so what's nice about this is that often, since you're putting a lot of complexity into the features, you can actually do with simpler models here, which makes it more robust, makes it easier to estimate when you don't have, a ton of training data and, things like that. One thing, of course, here that you need to do is you need to build that code book. I'm not going to go into too much detail about that, but basically, like the kind of at a high level, what we do is, for each of these songs that we have, we fit these, either a dynamic texture mixture or a Gaussian mixture or other mixture models. And we isolate all of these mixture components, and then, we have a kind of a clustering algorithm here that clusters not data points, but actual models, right? To kind of compress all these mixture components into like a smaller set of most representative, components, which are then, used as our, the words in our codebook, right? And so what's interesting here is if you look at, the same tags that we talked about before, and then, you compare the performance of the two models we looked at before with this, we call this a bag of systems rather than a bag of words, because each word is like this kind of generative model, right? So then you see actually that you do get that best of two worlds effect where, basically this model outperforms each of these other two, individually. So another thing that's actually quite important here is, I talked about this before, like especially when you have these more and more complex models, sometimes, if you only have like 100 songs in your training set for like some kind of, maybe more esoteric tag, often you don't have enough training data to fit these models well, right? But here in this case, the models are always very simple. And so one of the things that we actually see is that so these two curves that you're looking at here are from 0 all the way to 70 here are relative performance increase compared to these previous algorithms, right? This is two variations of the BOS system. I'm not going to go into detail about that, but the horizontal axis here looks at the cardinality of your training set. So this is tags where, we don't have a lot of training samples, and this is tags where we have a lot of training samples. And what you see is that for all of them across the board, we relatively increase performance, but especially for the tags where you don't have too many training examples, you're really improving performance, right? So again, saying that this is actually, you're building a more robust system here because of, kind of putting the complexity at the feature level and not at the, the model level necessarily. But so again, so the main goal here was really to combine, these multiple model classes at, multiple time resolutions. What's interesting here, again, as I said before, is you put a lot of complexity at the feature level, like when you're designing that code book, right? So then at the model level, you can use, kind of simpler algorithms that scale very well, that are robust and so on. But what's interesting as well here is that there's a lot of things that people then, use in text modeling that you can start using here as well, right? I mean, if you're interested in higher level structure, like, topic models, for example, hierarchical topic models, you can do all of that here now, right? With that representation. And also, I think what's important to realize is that to learn the code book, you don't need tags. So this is kind of like, a little bit aligned with, the whole story about deep learning, right? Where, you can kind of learn representation by just looking at all images out there. Here in this case, all songs out there, whether you have tags for them or not, it doesn't matter, right? You can use millions and millions of songs to kind of learn that code book and learn really good, code words, right? Which is great because, you have a lot of data, you use that to build really good features, and then after that, your model that you're going to be using is, a lot simpler, kind of, hoping that the features are capturing, a lot of the complexity already. As I said before, so we did extend this, towards video. I'm not going to go through this slide again, but just kind of I added one line to it here, which is that, what's nice about this type of approach is that you can easily do it with this heterogeneous data setting, right? Where if you have, video content and audio content, you can, make visual code words and audio code words, right? And kind of like mix that into that bag of systems representation. Just note that this is not kind of like, the standard computer vision type thing, because these are not, bags of prototypical features. These are prototypical generative models that generate this content, so it's a little bit different, right? Which, especially for video, is important because when you're looking at video, you're talking about a time series data, so you like to model some of that temporal dynamics again. So with these bag of systems, you're able to capture. You basically build code words that capture some of that, temporal dynamics. Of course, now one of the things here is that I haven't really answered is how do you get training data, right? How do we get our 500 example rock songs, for example? This picture is from inside Pandora a long time ago. That's how they do it. Now, when we started this, that's how we did it too. I mean, what else could we do? What we did is we didn't use, musical experts in the Bay Area, but we used undergraduate students. And so we built, a couple training data sets. In fact, some of them were derived from students doing annotations. Others were actually derived by mining some of the Pandora data as well. But clearly that was not necessarily the most scalable approach. So what we did is we actually kind of resorted to some crowdsourcing type approach where we built a suite actually of music games inside Facebook, which about 10,000 people engaged with these games. We collected data from more than 100,000 games, and eventually were able to actually build a system with performance very similar to a system built on Pandora-like data in terms of predicting tags for music. So basically the experiment that we did is we extracted a bunch of training data from here, and then we trained our system. Then we had another data set that we extracted from Pandora, and we trained our system, and then we compared which system is the best. And it actually turns out that within 1% of performance, these two systems came from one another. So which actually confirms that while from these crowdsourcing type platforms, you get a lot of noisy data, but if you average out over enough, because you get a lot of data, right? So if you average out over enough noisy data, you actually get pretty good training data. Question?
So this is where you got the labels. What was your source for content?
Uh-oh. Yeah, that is, let's talk about that one offline. Yeah, sometimes you have to be a little bit renegade, to make stuff happen. So there was actually, once we went public with it like that, there was a couple things that we did to, kind of play things a bit better. But when we started this research, it was certainly interesting. We did get a call at some time from a label that was telling us that we should stop downloading, so things like that. But over time, there's some mechanisms that you can do this in a cleaner way. But it's certainly one of the big challenges nowadays is still like how do you get this music data? There is a data set out there that a lab in Colombia that we collaborate with has collected in collaboration with a company called Econest. There's like 1 million songs they have in there. But the thing is, you don't get access to the songs. You just get access to the features that they extracted from the songs. And that by itself, from a research perspective, is still not really optimal. One thing I wanted to mention here was that, funny enough, so we did this research on, kind of crowdfunding. I'm switching words now, but crowdsourcing, training data. And so as we were doing that, a good friend of mine was starting this expedition to go to Mongolia to find the tomb of Genghis Khan there. I presume you've all heard of Genghis Khan. So one of the big mysteries is where his tomb is, and they wanted to find where it is to then make it like a World Heritage Site. And so, he had bumped into this company that gave him literally 100,000 satellite images. But he's like, I can't really look at this. I'm going to have to spend 100 years looking at all those to try to figure out where possibly, the tomb could be and then organize an expedition. So we came up with this idea to collaborate with National Geographic to actually crowdsource the collection of tags for these satellite images. And so as my friend was on the field in Mongolia, we back in UCSD were working with National Geographic to collect these tags and over satellite send them to their iPads on the field to kind of guide the expedition towards, where in a certain area in Mongolia there could be ancient tombs, possibly the tomb of Genghis Khan. And so that was a very interesting kind of collaboration that came out of that, which then actually led to one of my students who was deeply involved in this, starting a company called Tumnod, which does crowdsourcing for satellite images. Got acquired about 2 years ago by a company called Digital Globe, which is a company that has access to an insane amount of satellite data. And the reason why I'm mentioning this here is because I don't know what to do with it yet. Like it's a humongous amount of data these guys have, and especially nowadays, this is getting a very hot field. I mean, with Orbital Insight and companies like that, analyzing satellite imagery is becoming really big. So anyway, so there's kind of like interesting opportunities there too. If anybody's interested in that, I'm happy to discuss offline. But anyway, so back to music. So as I said, so now we have this annotated database. We can do, semantic recommendations with it. We can do basically query-based recommendations, kind of like, you have a song, you extract the tags from the song, and then you recommend songs with similar tags, kind of the Pandora system. But as I said, so Pandora has this problem that they're kind of limited to the songs that, they can manually index, so they have a smaller database. There's other, systems out there too, like iTunes. But the thing is, like for example, with iTunes, which used to be called Genius, so they actually don't do much content analysis, as far as I know. It's hard to tell what Apple really does. But they are more of like a collaborative filtering type system, which is people who bought this song also bought that song. But so the problem with that was when we uploaded the music that we recorded in our garage, it was not able to give us any recommendations because clearly nobody had bought our music, right? So anyway, so kind of just contrasting with those systems, I mean, Pandora doesn't really, allow much text-based search because that would mean that they're giving away all their data. iTunes can't really deal with relatively unknown music. With the systems that we built, you can actually do all of the above. You can do, you can seed your query with, or you can make a query that is based on, a seed song. You can make a query that's based on text. I mean, whatever you want to do. So it's certainly a very flexible system. We once compared this also to iTunes Genius. I'm not going to give you the details here, but so these systems are actually, they're very different, collaborative filtering system versus, a content-based system. And it was actually very interesting to see how, you'd expect that this would easily outperform this type of system, right? Because, I mean, by the end, people who bought this song also bought this song. I mean, that should say a lot about, kind of similarities between songs. But actually, it turned out that we were able to, provide recommendations that were of, similar quality through a user test than what iTunes Genius was doing. So we did a little bit of real-life testing as well there. So it was kind of very encouraging to see that these content-based systems were actually doing very well, compared to some of these real-life systems. Now talking about this, query by example setting, or kind of more in general, this collaborative filtering setting. So the idea, so in query by example setting, the idea is you're given a song or multiple songs, right? And then the question is, can you build an algorithm that recommends you like another 20 songs that are like that, right? And so what iTunes does, as I said before, is this kind of collaborative filtering approach where, given a song with a certain set of users that likes it, well, maybe we'll recommend another song that has, similar users that like it, right? But as I said, so the problem here is that like when, I upload my song from my GarageBand, then, if they've never sold it and users have never listened to it, it's very hard to, provide good recommendations. There's also other issues that they have, like for example, popularity bias. Some of these systems really kind of, keep pumping very popular music into playlists all the time, and companies want to steer away from that. So what we want to do is we actually want to kind of, complement collaborative filtering with audio content to improve these, recommendations or bypass challenges like on new content, right? And so one of the things that you could do is you could say like, well, let's just, look at the actual audio content and do like some Euclidean distance metric between these, whatever audio features, and, maybe that, gives us something. But the reality is it doesn't work very well, actually. Like, for example, you could have two songs that have each a 30-second silence in it, but that doesn't mean these songs are similar, right? So what works a lot better is if you actually first annotate these songs with tags and then, make recommendations based on songs having similar tags, basically the kind of the use case or the example that I gave before, right? But I wanted to mention this because like we actually did experiments on that, and I'm not gonna like explain this whole kind of graph here, but the thing is that, so this experiment here, the one down here, is an experiment that is based on kind of directly computing distance between audio features. And the one up here is one where you're, using the tags to make recommendations. So you're actually, computing distances between tag vectors. And the horizontal axis, the more to the right is the better. So you can see that actually using tags for recommendations does better than using just audio feature similarity. Now, that said, I mean, there's a lot to go still to the right there, right? So we can still try to improve this thing. The bottom line is really that, like, by the end of the day, the audio signal must have, the information, right? I mean, if you go to tags, you're going up a level of abstraction, so there's some information you're throwing away. So somehow, like, so what's happening here? Like, why is, just computing distance metrics on these, audio features not working well? Well, it's because there's lots of noise. But what if we can filter out that noise? What if we can do some sort of kind of feature learning step here where we filter out the noise and we extract, the most meaningful features, right? And so this nowadays in machine learning community is often called, metric learning, where you're trying to learn, what's the kind of best transformation of your feature space to, address a certain problem. But so the point here is we want to do that learning step to extract the most meaningful audio features and then see what happens. Can we do better, right? And so basically the setup is the following here. So you have a space now. Now in this case here, all the dots are individual songs, so they're no longer features, right? So you have a space with songs, bam, like a bunch of, training songs, for example. And so the deal is the following. Let's say that one of these songs is your query, right? Then kind of the mechanism that we're looking at here is that you would rank the other songs by distance to the query to basically come up with a similarity-based ranking. But the reality is that if you actually reveal, which songs, the ones with the plus here, are, more relevant to the query song, and the ones with the minus here that are the ones that are less relevant to the query song, if you reveal the truth now, you see that actually what you end up getting is a ranking of songs that, kind of on the top of the ranking has some relevant recommendations, but some very irrelevant recommendations. And the reason why this happens is because this space is just the raw audio space. Like, there's lots of noise in there. What you would like to do is you would like to learn some sort of transformation of this space that pulls the relevant recommendations closer to your query and pushes farther away, the irrelevant recommendations. Because, like, for example, in this space, if we do a distance-based ranking, it would actually put all the relevant recommendations higher ranked than the irrelevant recommendations for this query song here, right? So what we did is we devised an algorithm that, does exactly that, that learns the transformation of this space, to obtain better rankings induced by distance. Now, you may say, like, oh, I've seen this before, right? I mean, people have done metric learning and machine learning for several years now, so what's different here? Well, the big thing that is different here is we're optimizing rankings. This is not like a classification algorithm or something like that. This is actually a ranking of songs. So now you're trying to optimize things like, mean average precision or NDCG or, precision at 10, like typical ranking measures. And those measures are actually not so simple to optimize because they're very kind of combinatorical in the way they behave sometimes. So this is not a simple problem that can just easily be, generalized from, metric learning for classification. So anyway, so we devised an algorithm here that basically allows to learn this transformation W, and without going into the mathematical details right now, what I would like to tell though is that, this algorithm does support this kind of large variety of ranking losses, and that is at that time, was a very novel contribution to actually optimize ranking losses with respect to, a learning algorithm like this. The other thing, of course, is that, since you're optimizing rankings, you're kind of comparing good rankings, that's the green thing here, with worse rankings. And if you want to do that for every possible pair of rankings, you get an exponential number of constraints in that optimization problem, which can become, very burdensome. So you have to come up with some cutting planes or similar type algorithm to make that, more efficient to compute. So anyway, so at a high level, this is a metric learning algorithm, but it optimizes rankings, which is, exactly what we want to do. Now, looking at the, the experimental results here. So remember these from before, right? So the one up here, right? That was the one that had used the tags, and this was the one that used the audio features, right? Everybody remembers? So what we're doing now is we're going to hit both of them with this metric learning to rank algorithm, right? I mean, you could also, you could start from a tag vector and learn a transformation to obtain, better rankings of songs. Or you could start from a bunch of audio features, right? And then learn a transformation to come up with a better ranking of songs, right? So if we start from the tag vectors and you throw that MLR algorithm at it, you improve your performance. Okay. If you use the raw audio features and you throw the MLR algorithm at it, you improve your performance. But the interesting observation is here that actually starting from the raw audio features, you can improve more, which somehow makes sense because if you start from the raw data, you're really not throwing anything away. When you go to tags, then you're already throwing some information away, right? So somehow now the roles are flipping around here. So it actually turns out going with raw audio features that you optimize for according to these ranking problems, you can actually do better than based on tags. Okay. So that was a very interesting observation. Now that said, we can do even better because we could actually, instead of just using tags or just using audio waveforms or audio features, we could just do both, right? And so that's certainly kind of work that I've historically been working on quite frequently, which is instead of learning a transformation in one space, how about let's learn transformations in different spaces at the same time? But how about if besides the actual audio waveform for the song, we also have access to all this kind of information, blogs and videos and pictures and social network information and things like that. Right, so using these type of algorithms, we can actually, learn transformations in a bunch of spaces in parallel, and at the same time also learn which, data is relevant and not, to kind of address this problem. So we implemented this, in real life for music videos. That's again within the context of the company that my students started, and we've been getting some, pretty good feedback about that to date. What's cool here is actually the reason why I was mentioning this is that. So we're extracting videos from YouTube here, and literally like this, with this one, we really achieved our initial goal. Our initial goal, I didn't mention this, but for us when we started this, we wanted to recreate Pandora in one day, rather than 1 decade. And so we actually did this. We extracted 1 million songs, music videos from YouTube, and annotated them in 1 day, and bam, there we went. Right, so that was kind of like an interesting long-term goal that was achieved. And then, in the last part of the talk here, which is kind of very short and very high level, but so I still really want to mention that, everything we talked about up till now is really, in my opinion, mostly of academic value. Because again, if you really think about how the user wants to interact, not just with music, but with video and with all kind of other entertainment content, maybe even restaurants and things like that, is the optimal system is a system that just brings the content to us without any search query. Right, and so rather than having the user provide information that they're working out or that they want to listen to some very intense music, so to speak, to then generate these playlists, what I would like to do is kind of drop all of this and basically replace it by extracting information from these sensors that we wear on us to figure out what am I doing, how am I feeling, and then base recommendations on that. Now, of course, it can never be zero touch. I mean, you have to have something like thumbs up and thumbs down from the user, sure. But that's the kind of information the user doesn't really mind to provide, right? It's just that, you don't want to kind of push them into like a Google type search query, or you don't want to ask them like, give me, 3 songs that you would like to listen to right now. It's not always easy, right? So anyway, so that's what we're currently working on. And what's nice about this is that the algorithms that we built to annotate music, well, are essentially time series, are algorithms to model time series and annotate them, right? So we can actually use them as well with, of course, some modifications at the feature level to annotate accelerometer data, microphone data, gyroscope data, and things like that, and then basically kind of match tags from one against the other as a starting point at least, and then use the thumbs up and thumbs down to refine, this kind of the relationship here, because clearly how that and that relates will be a very personal thing, right? Depending from user to user. But anyway, so that's what we're doing nowadays, not just with the smartphones, but also smart watches now, and also looking into like textual data, like tweets and other text that people put into their phones, because that actually reveals quite a lot of interesting information. I know. So this is. I once talked about this to one of the newspapers down in San Diego, and got a lot of responses that this is kind of creepy, and I don't disagree, to be honest. But I think from it's all about let's first solve the research problem, right? If we can actually use that data to make really interesting predictions, then we can go to the next step and think about privacy and things like that. But so anyway, so that's what we're currently working on, which pushes us into the interesting space of having to write IRB proposals for human subjects. The NIH that I traditionally didn't really raise funding from that frequently, but it turns out that they're very interested in that as well, and several collaborations with the medical school, ranging from, actually I think I have a couple examples in here of the kind of so this is again like the same thing. It's basically this multimodal signal processing and machine learning to predict a bunch of these activities. What's interesting here as well is that we're not just interested in predicting standing, sitting, sleeping. I mean, we're interested in very kind of precise predictions. People are vacuuming or doing something or something. I mean, this is, detailed level activity prediction. I think that's where, it gets very interesting. Of course, we have to collect training data for that, and that, one of the things that we do through these collaborations with the medical school. But so by the end of the day, what you want to do is these sensors figure out what your user is up to, and then you automatically generate, a playlist based on that. And because of, I didn't say this in the beginning, but so some of these slides I had to whip together very last minute because my presentation was wiped out this morning. My keynote shut down on me, and I lost all files for my presentation. So sometimes I don't know which slide is coming next. So I'm not sure whether this is the last slide, but I think there may be a couple more on some of these, medical applications. But so quickly, so we're, working on some physical activity tracking projects, working with some people, some surgeons that actually are interested in tracking their patients after a surgery, because what happens is you do a surgery, 3 weeks later you see your patient. You ask the patients, how have you been? How well have you been sleeping? And how active have you been? And people will tell you what they did yesterday, but they will not remember the last 2 weeks. And so with this here, with these devices, you can actually, track these patients and then immediately kind of, give the, the surgeon or the doctor, a more detailed report. You can use it for rehabilitation, tell people like, hey, you need to do your daily activities to make sure your bone grows back together. Monitoring for mental health, very important, not necessarily to detect that it's happening, but to predict that it could happen, and then maybe, through an intervention, prevent somebody from getting a bad dementia attack or, starting to drink or things like that. This is a very interesting project as well, where we're trying to help migraine patients who, as you may know, I mean, migraine, there's some other diseases like IBS, sometimes, major depression. So there's some of these conditions that are heavily influenced by contextual factors, like, it depends on what you eat, what you're doing, whether you were on a plane, whether there was a high or low pressure system going over you. It's not often all just very well understood. And what doctors are trying to do is they're trying to figure out, basically, what did you do today and what were you exposed to? Of course, that's a lot of questions, right? But it turns out that actually, the old system, which is, keep a personal diary, is completely, inadequate to try to help these migraine patients to figure out what it may have been that caused their migraine. In collaboration with a company, we're kind of looking at, questionnaires of up to 300, 400, 500 questions about what people eat, travel habits, sleeping habits, and things like that, to figure out whether there's any correlation with their migraine attacks or these other type of conditions. But the thing is now that we have these wearable sensors, we can actually use that to make it a lot easier for these people to collect that information. I tell you one thing though, with migraine patients, so one of the clinical trials that we did involved them answering 300 questions 3 times a day, and I tell you they're doing it because they're desperate to get better. But imagine what more we can do if we can actually tie it in with, these wearables, right? Okay, reached the last slide. Now. So just thanks to everybody who's funded me and who's worked with me in my lab. Thank you.
Thanks so much. We have time for questions. We use the mic so it gets on the recording. I'm going to take presenter's privilege of asking the first question. I was really interested in the mixture of the different generative models to do the classification of the audio signal. Do you have any idea how often you get mixtures of, say, more than 2, or how often are there 2 models in a classification, and how often are there more than 2 to represent a song, or just depend on how long the song is, etc.?
Oh yeah, no, you get basically since the different models. So you can only have a Gaussian really compete with a Gaussian, right? You can't really compare the likelihood that you get for a Gaussian with the likelihood you get for one of these temporal, models. So I think, Ram, you asked the question along those lines. It's like you kind of look at all these different models in parallel as parallel code books. So by the end of the day, as you're counting the occurrence of these models in the songs, you actually do get a lot of occurrences of all of them all the time, right? So it's like kind of you're reading a text with words from different languages, and you're considering the dictionaries for the different languages in parallel, right? But again, still wherever there's a word, it's one language, while here you can still have that overlap because you can look at one piece of audio in different ways. right? So we somehow have control over that, but we like it to have a large variety of different models that are firing, to model the song. So, wait, I think you have to.
My question is about the manual tagging of each song. So probably each subject will provide some typical category of music such as jazz or classic or something. And is there any initial dictionary before initiating the process to ask for each subject to assigning some labels? For example, unless providing initial dictionary, each user will make his own word to tag each music, and how to say, discrepancy between each users can easily happen. And
so there, you kind of put a lot of questions into one question. So one thing is to kind of jumpstart the crowdsourcing. We actually used our mini Pandora version. That's one thing. We did quite a bit of research initially on kind of basically fixing the initial dictionary of 200 to 300 different tags. As you said, it's certainly totally true that different people will make different tag associations. This is one of the challenging things with music. It's not like you look at a picture and it's a Coke can that's sitting in there. No, everybody sees a different color, right? And what's interesting of embedding this into Facebook is that at least at the time when we did this, you could actually extract demographic information as well, from Facebook. So we had these kind of interesting things. Like one of the things that we noticed was that, the agreement about which song is danceable and not danceable was very high amongst one gender and was very low amongst another gender. Now you can guess which one was the one that had the high agreement about which songs were most danceable. What do you think? Males or females were in high agreement about which songs are danceable? Who thinks it's females? Who thinks it's males? Oh wow, there's no conclusive answer. It was actually females. So female Facebook users basically were on very high agreement, like on which song was danceable, which one was not. And with males, it was all over the place. That's just one example. So there was a bunch of interesting demographics we could extract from that. When we initially did this, the thing is, there's a lot of factors that go into this. Like if you start thinking about subjectivity, then you want to think about how can I cluster users that have a similar type of way of interpreting music and things like that. Initially, when we did this, we couldn't do that. It's like you just have to look at the high average level because you start there, you build good models there, and then you start to kind of refine that. But that is really something that we have started to look at, over time as well, how you can kind of build, kind of clusters of users that have different ways of, looking at this content. And then last thing I think that you were talking about as well is that, you can allow users free text to tag these songs. So we actually had a couple of games that allowed users to kind of basically provide their own words because we wanted to grow our vocabulary as well, but in some sort of controlled way, right? Say again?
Can you repeat the question?
Yeah, so the question is what the final dimensionality of the tag vector was. So it was somewhere between 200 and 500, depending on which stage of the research. But I think today we're closer to the 500, but initially it was like 100 to 200 that we were at. So.
This might be kind of a tangential question, but I'm wondering, I know music has certain patterns and things that are easily comparable between songs and even genres, but how much do you think that these models would be applicable to spoken audio, like radio broadcasts, podcasts, that kind of thing?
Yeah, very interesting question about applying this to spoken audio. So the thing is, the field of speech recognition is its own big field, and we certainly wouldn't want to attempt to kind of go in there. Like for example, with Kivio, we have another startup company that we're talking to for kind of processing all the the spoken language. in videos and transcribe that into text. Now that said, when you're talking about spoken audio, it's not necessarily just about what people say. There could also be things about like, well, maybe, which speaker is this, or what type of speaker, or what is, like, one thing is trying to figure out what the person is saying, but the other thing is trying to figure something out about the timbre of the voice of that person and things like that, right? Or also like, environmental sounds and things like that happen while, the person is speaking. And that, once you go down that path, then yes, we can really, apply these techniques to that as well, right? But transcription, that we have not, kind of clearly decided not to go down that path. Although some of the features that we use are features that they use for, speech recognition.
Thanks. An interesting talk. Two questions which I think are related. The first one is when we move into the world of the arts, we come upon issues of, when we try to type things, of at the one end parody, where someone is taking a form and actually sending it up, but in order to send it up. So, and the other end of that is pastiche, where people are saying, well, this is a sound everybody likes, so I'm going to just produce a generic version of it. And one, I guess, related issue of that is you get a kind of Goodhart's law function. If you discover what people are liking, you just create crap that goes along because it models that. But at the other end of that question then is also, have you thought about the ability of this system to write music, given that if it understands the tagging of music?
Yeah, that is, oh boy. By the way, points well taken about, inserting what people want to hear. I've talked to several music producers about this, that's how they, make commercial music. They take an artist and then they reproduce the thing, inserting exactly those kind of things. So, and clearly what's nice actually about this type of system is that you can actively steer away from that, because with the tags you have a handle on what's happening in these songs, so you can create that like a serendipity effect in a listening, or a surprise effect in a listening experience. We can really go from a rap song suddenly to a classical song and then discover that this user likes that transition, for example. While most of the time when you follow collaborative filtering type approaches, that's these kind of weird jumps are kind of less likely to get modeled, right? But to go back to your question about music synthesis, I mean that's a hard problem. I know people that are looking into that. We have certainly not tried it. One thing that we could try is kind of looking at small audio clips, for example, and then using our technology to kind of and our algorithms to describe these snippets and then figure a way of how can we combine them. But then still, combining means you have to still transition from one into the other and figure out how to kind of glue them together and stuff. So, I know people that look into this. I know it's still a pretty hard problem to very hard problem, and we have not attempted to do that, but certainly very interesting. Right? Imagine, like, for example, for medical applications, that you could write a song on the fly that kind of guides a person from in a bad mood into a happy mood or something like that, so. Yeah, totally, yeah. That's the risk of the research. Yeah.
Well, following up on that thought about the crowd as a herd, your tag about exercise music, I always wish that Pandora had that, and they actually don't. I was trying it again this morning without any luck. So have you looked into, or how flexible is your system at, say, you wanted to add, double the number of tags to a set that isn't there currently, but a new set of semantic options? Would it be able to do that relatively easily, or not at all?
Yeah, totally. So in order to do that, it's all about training data. As soon as we get the training data, we can basically immediately do it. So the nice thing is that actually it turns out that these systems don't need thousands of training songs. Actually, for some of these tags, like even with 50 to 100 training songs, you can already get somewhere. And then once you get somewhere, you can kind of build a system that bootstraps itself a little bit, like active learning and things like that. So most of the time when that happens, so either you go to the crowdsourcing platform and you really try to kind of actively collect more examples for these tags. But what actually most often happens nowadays is that, because a lot of that what we do is actually through Kivio, through the company, it turns out that we talk to companies that do have, most of the time when they have tags that they're interested in, they have to express that to us in some way. And then they're like, well, it's this set of songs that exemplify what we mean with that tag. So we actually get the training data from them, right? And as soon as they can do that, then we can literally just add as many tags as they have data for literally overnight. So, so that's pretty easy. There's also, like, what I haven't talked about here is we also have algorithms where we look at correlations between tags. You know, if you have a song with, like, you know, an electric guitar, it's likely there may be drums in the song too, so these tags are often, you know, correlated with each other, so you can kind of also try to capture that in the model. And then, you know, very often with actually very few examples of songs for a certain tag, you can kind of generalize that way too. You know, but so the direct answer is either, you know, we pump it into the crowdsourcing engine, or what happens most frequently is that people actually show us examples of what they mean with a specific tag. Because they come up with very esoteric tags sometimes, and so we are like, we don't even know what you mean with that, so you're gonna have to give us some examples, you know.
Okay, I think we should wrap it up. So let's thank Gert again. Thanks so much.
Thank you.